this is the final exam for spring 2023 of MA 265. And let's start with the first problem. We have this linear system governed by three equations, and we're trying to find which value of A does the system have an infinite number of solutions. So the first thing we can do is put this into matrix form. So we want to put it into an augmented matrix form. So this means we take the coefficients of all these variables, and hopefully you have some experience doing this throughout the entire semester. So we have, in the first row, we have 1, 1, and 2. And then that equals 1. And then in the second equation, we have nothing for the x, 1 for the y, and a for z, setting that equal to 3. And then we also have 4, 6, a squared, and a plus 6 for the third row. Now, when we want to find what value of a the system has an infinite number of solutions, this means that we're going to have one row of all zeros, because that means we're going to get a free variable, which can be anything, so then there's going to be infinite solutions to the system. So I think maybe we can, again, just as a recap, say, for example, we have this matrix here, and then this is equal to 0, and this is like a or b or something. Then notice that these equations just become x equals a, and then y equals b, but z can be anything. So z can be like any number. So this means that this system, for example, would have an infinite number of solutions because of this row of zeros in the augmented matrix. So what we want to do is we want to row reduce this down to see if we, to see for what value of a we get a row of zeros. So just to do some simple row reduction, I'm going to take the third row and then subtract 4 times the first row, and that gives me 0. 6 minus 4 is 2, then a squared minus 8. And then that's going to give me a plus 6 minus 4, which is a plus 2. And then I'm also just going to simultaneously do, after this step, I'm going to do R1. So first I did this step, and then after that I'm going to take the first row and then do R1 minus R2. And that gives me 1, 0, 2 minus a. And then 0, 1, a. So the second row stays the same, so 0, 1, a, 3. And then 2 minus a. And then we have, again in the first row, 1 minus 3, which is negative 2. Okay, and then I'm going to then just do the third row, and then take 2 times the second column, and So I'm going to take the third row and then subtract 2 times from the second row from it. And that gives me, the first row stays the same. Same with the second row. 0, 0, a squared minus 8 minus 2a. And then a plus 2 minus 6, which is a minus 4. Okay, so first of all, we can just focus on this row now, because we see that this is the row that we can solve most easily to find if there's a row of zeros. Because these other ones, we already have pivot values in these entries. So we're looking at this last column, and so we're trying to find when this last column will have a squared minus 8, a squared minus 2a minus 8 equals 0, and also a minus 4 equals 0. So we want both of these conditions to be satisfied, so you can see that both of these are satisfied when a is equal to 4. So our answer is B. And this gives us this row of zeros on the bottom, which means the system will have an infinite number of solutions. Okay, so in this problem we have this set of 3 vectors that is a basis for r to the 3. And we want to figure out for what value of a is this satisfied. So basis, recall, means that there's going to be linearly independent vectors that span r to the 3. So that means that these vectors must be linearly independent. Okay. Now, one way to approach this is you can literally plug in these values of a that that are in the answer choices. So for example, you have a equals 1 or negative 1, and then you can see if those vectors are linearly independent. So because you're not given that many choices here for a, you have like 1, negative 1, and 2, I think it'd be pretty quick to do that process. So for example, if we plug in a is equal to 1, you would get the set of vectors 1, 0, 0, 1, 1, 3, and 1, 1, 3. So obviously these two are not linearly independent. So this is not a linearly independent set. So it's not a basis for R to the 3. So, for example, already from that, you can see that this is definitely a condition that must be had. So we can eliminate C, D. Yeah. Then, for example, we can also plug in A equals 2 and do 1, 0, 0. That gives us 2, 2, 3. And then 1, 1, 3. Wait, no, 1, 1, 6. Okay, so from this, I guess if you wanted to do some simple reduction, you could see that, if we can subtract 2 times this vector from this vector, which will give us, the vectors 1, 0, 0, 0, 2, 3. And let's say we also subtract this vector from this vector, 0, 1, 6. And, these are not multiples of each other, so it's kind of, that tells you that this is a linearly independent set. So this kind of simple manipulation where you just look at these vectors and you kind of do some linear combination making in your head to figure out if these are linearly independent, that's another quick, maybe faster way for, like, on a final to figure out if these vectors are linearly independent or not. And so this tells you that A equals 2 will form a basis. So this is not, the fact that A is not equal to 2 is not a condition where you wouldn't have a basis. So that means that we can eliminate E. And then for -1, we would have pretty much the same thing as A equals 1 except negated. So we have 1, 0, 0. Then A3 is -1, -1, 3. And then we have 1, 1, -3. Okay, so looking at these two again, notice that they're just linear combinations of each other. We multiply this one by -1, and then we get this vector. So this means that this is, again, not a linearly independent set because these two vectors are not linearly independent of each other. So that does not form a basis for R3. So this is another condition where A cannot be -1, or else you won't get a basis for R to the 3. So both of these conditions are satisfied, and so both of these conditions are needed for there to be a basis for R to the 3. So we know our answer choice is A. Okay, so another way to do this problem is, perhaps a more formal way to do this problem is if you write this in matrix form. So 1, 1, 3A and set equals 0. So there's this test called the test for linear independence, right, where you have some scalar multiplied by your first vector times another scalar multiplied by your second vector, and then this third scalar multiplied by your third vector, and this is equal to 0. So this test states that this is only true if C1, C2, C3 are equal to 0. And if that is the only solution for this equation, then you know that the V1, V2, V3 are linearly independent. So that's what another test that you can do here. So if I do row 1 equals row 1 minus row 2 and row reduce this, I'll take 1/3 of row 3 as well. 1, 0, 0, 0, 0, 0, 0, A1, 0, 1A. Okay, so then you can see that if A is equal to 1 or -1, then these two rows will be linear combinations of each other, right? Because this means that this turns into 1, 0, 0, 0, 1, 1, 0, 1, 1, or for -1, or for A equals -1, you would have -1, -1 here, equals 0. So in this case, you would be able to eliminate one of these rows, right? And this would leave you with, something up here, 0, 0, 0, something up here that's non-zero row, and then you would have a row of zeros. And this means that, okay, I should just write out what these are. So for example, let's just say for A equals -1, you would get 1, 0, 0, 0, -1, 1, and then a row of zeros. And this row of zeros means that you're going to have infinitely many solutions to this expression. And if that would mean that these vectors are not linearly independent. And so for you to not have any rows of zeros in this matrix, then you need to have A not being 1 or -1. So that's another way of approaching this. Okay, and that's problem 2. For 3, we have find all possible C such that the nullity of the following matrix A is 1. So if the nullity is the dimension of the null space of A. Okay, so the nullity is the dimension of the null space of A. So this means also that we have one free variable. So the reason we have one free variable is that the dimension of the null space of A is spanned by only one vector then. So that means that there's only one free variable that is the spanning vector of the null space. So this is how we know that there's only one free variable. So what we would want to do then is find for the null space, you have ax equals 0. We would want to find for what value of c is there only one free variable. So we can write this in our augmented, or our matrix form. So we write this expression here. Okay, and then we can start row reducing. So maybe the first step is to do row 2 equals row 2 minus 2 times row 1. And then I guess I'll do the same thing with the bottom row, where I'll do row 3 is equal to row 3 minus 2 times row 1. And that gives me c minus 2, 0, 0. And then 0, c minus 4, 6 minus 4 is 2, so that's 2, 0, 0, 0. This top row stays the same. And now we can kind of just look at what we have here. First of all, we can notice that we have a row here that could suspiciously be 0, a row of zeros, if c is equal to 2. So if c is equal to 2, then we'll have this will become 1, 2, 2, 0, 0, 0, 0, 0, 0, 0, negative 2, 2. Okay, so hopefully you can see that these two rows are not multiples of each other. This means that they're linearly independent, so there will be no more rows of zeros. So this single row of 0 means that there's one free variable. And that means that the nullity is going to be 1. So off the bat, we can eliminate A, C, and that's it. Okay, and then from here, I guess the quickest way would be to look at your answer choices. So if you look at c equals 1, if c is equal to 1, then you have, okay, if c is equal to 1, you have 1, 2, 2, 0, 0, 0, negative 1, 0, 0, 0, 1 minus 4 is negative 3, 2. So these rows are not multiples of each other, or they cannot be written as linear combinations of each other. So we know that c equals 1 is not a case where you'd have a nullity of 1. You would actually have a nullity of 0 because you don't have any rows of zeros, so you have no free variables. So this eliminates D. Then if we look at c equals 6, you can see that it would give you 4, 0, 0, 0, 2, 2, and 0, 0. Notice that you can actually row reduce this further. So if we subtract row 3 from row 1, we get 1, 0, 0, 4, 0, 0, 0, 2, 2. And then furthermore, we can see that these two rows are multiples of each other, so that we can eliminate one of these rows to become a row of zeros. So, this would be row 1 equals row 1 minus, say, 1/4 row 2. Oops. Okay, so again, you see this row of zeros, and these two rows are not multiples of each other, which means that you will not have any more rows of zeros. So we have one row of 0, which means we have one free variable, and that means that the nullity is going to be 1. So for c equals 6 and c equals 2, we get one row of 0, which gives you the one free variable, which again corresponds to a nullity of 1. So our answer is E. Okay, in this problem we have a 3 by 5 matrix with rank of A being 3. Which of the following statements must be false? So first of all, rank of A is equal to 3. This should tell you that the row reduced echelon form of A will not have any rows of zeros, because it will have a pivot entry for every single row, because the rank of A is equal to the number of rows of A. So just to visualize what's going on here in this ax equals b equation, I don't know if I read that one, but it's just saying that for any b in this equation ax equals b, there will be a solution. So we're going from A, which is a 3 by 5 matrix, so it has 3 rows, 5 columns, and then that is multiplied by x, which is going to be a 5 by 1 vector. This is because of the rules of matrix multiplication. It has to be 5 by 1 because just you need to have the same number of terms here as the multiplying here. And so that will give you a vector b, which is a 3 by 1 as a result. Okay, so if A has a rank of 3, we can visualize this in the augmented matrix form, where we have, A on the left, and then B is over here. So looking at that, our B could be any numbers, but we know that our A is going to be rank 3. So we know that it has a pivot entry in its reduced form. So in its reduced form, we have something like 0, 0, 0, 1, 0, and then 0, 0, 1. And we don't really know what these entries are because there's more variables than there are number of rows. So from this, you can see that there's no row of zeros, which ensures that there will be a solution for every possible b in R to the 3. This is because every variable here has every relevant variable for the 3 by 1 space has a pivot entry. And this means that you will be able to have a solution for any possible b because these 3 variables have a pivot entry. So that means that this statement is true, so this is not the answer. So our second choice is if B is a 3 by 5 matrix that is row equivalent to A, then the columns of B transpose are linearly independent. So if we think about this, we have B is a 3 by 5 matrix. So row equivalent just means that it can be exchanged into the other matrix. So B can be exchanged into A by a simple by a series of row operations. So it just means that B is a version of A, but you just have done some row manipulations to it. So B is a 3 by 5 matrix, right? So it's row equivalent to A, and we're trying to see if the columns of B transpose are linearly if the columns of B transpose are linearly dependent. So if this is B, B transpose is going to be flipping it over so that you're exchanging the rows and the columns. So that means that you're going to have a 5 by 3 matrix. So you're going to have 5 rows now and 3 columns. So we know that A has a rank of 3. So because it has a rank of 3, kind of like you can see here, it's going to have 3 linearly independent rows because you have a pivot entry and then zeros in all the other positions in the other vectors. So for example, you have a 1 here, a 0 here, a 0 here. There's no way that you can write that as a linear combination of each other. Same thing with this one, you have a 1 here and a 0 here and then a 0 here. So by that argument, we know that B is going to have linearly independent rows. So these rows are linearly independent. Well, when we just take the transpose of that, we're just getting something like this, where the rows are now flipped into the columns. So because of that, since the rows are linearly independent, then the columns now in B transpose, are going to be linearly independent as well, because we're just taking the transpose, we're just flipping the matrix around the diagonal. And because B is row equivalent to A, it is essentially, it retains the properties of A, where the A rows are linearly independent. So B will also have linearly independent rows. So because of that, and that this transpose is going to have linearly independent columns and not linearly dependent. So this is the false statement. Looking at the third option, if B is a 3 by 5 matrix that is row equivalent to A, then the row space of A equals the row space of B. So this is going to be true. Why? Because so the row space of A is the span of the rows of A. And kind of like we talked about here, the span of the rows of A, please ignore that. So the span of the rows, so even though we have A as this matrix and then B is some reduced form of A, the relationship between the rows of A and the rows of B, they're preserved through row operations. This is just a property of row operations because all we're doing is just adding or subtracting or multiplying them by a scalar and then adding them to other rows. So because of like the linearity of the row operations, the relationship between rows is still preserved. So the relationship between rows in A is going to be still the same as the relationship between rows of B. So that means the span of the rows of A is still going to equal the span of the rows of B, because like fundamentally they're linearly independent and they're only differing by row operations of each other. So because of that, we do know that the row space of A is equal to the row space of B. So this is false, or this is a true statement, so it's not the answer choice we're looking for. In part D, we have the linear transformation, excuse me, x to ax is onto. So onto here, it means that the span of the columns of A is going to be, in this case, r to the 3. So it's r to the 3 here because obviously the columns of A only have 3 elements in them, so they can really only span r to the 3. So is this true? So we look at A, right? So we know that A has these 3 pivot entries. And so we see that we already have 3 vectors. So the columns of A are going to be 1, 0, 0, 0, 1, 0, and 0, 0, 1. And then these other 2 random ones that we don't know, but we don't really care about because we already have 3 linearly independent columns here that will span the entirety of r to the 3. So because we know that A has rank 3, we know that these linearly independent columns are going to exist because of the pivot entries. And so that means that it is an onto transformation. So this is a true statement and it's false. It's not the answer to this problem. Okay, here we have this linear transformation defined by A transpose X being so the linear transformation defined by A transpose X is 1 to 1. So 1 to 1, first of all, let's just look at what that means. So that means you have 2 vector spaces A and B. You have say vectors in A and then you have vectors in B. If it's 1 to 1, then each vector will map to a unique vector in the B vector space. What cannot happen in a 1-to-1 transformation is if 2 vectors in A, 2 or more vectors in A, map to the same vector in B. This is not allowed. This means it's not a 1-to-1 transformation. So we look here now at this transformation, A transpose times X equals some vector B in the B vector space. So just looking at the dimensions so we can visualize this better, A transpose is a 5 by 3 matrix, which means that you flip it along the diagonal. So the 3 by 5 matrix becomes a 5 by 3 matrix. This then multiplied by X, so X has to be a 3 by 1 matrix because of the rules of matrix multiplication. The dimensions have to work out. And then B is a 5 by 1 matrix. So one property of a 1-to-1 transformation is that the columns of the transformation matrix, which in this case is A transpose, needs to be linearly independent. Okay, so because we know that the rank of A is 3, A transpose is going to have 3 linearly independent columns. That's kind of what we were arguing for the answer choice B. So because we know this, I think one way that we can visualize this, so we know that the columns of A transpose are linearly independent. This means then, because 1-to-1 transformations have the transformation matrix as having linearly independent columns, we know that this linear transformation is going to be 1-to-1. So we know that this statement is actually true. Another way to visualize why the linearly independent columns mean that the transformation is 1-to-1 is to kind of think of it like this. So we know that A transpose has pivot columns, or is going to have a pivot entry in each column when we row reduce it. So, say that our A transpose is going to have some form like this, where, you see how these columns are linearly independent, and as we know that this is row equivalent to, that this matrix is going to be row equivalent to whatever A transpose is going to be, because we know that A transpose, is going to have pivot entries, one pivot entry in each column. So, say A transpose is something like this, and then our X matrix is like X, Y, Z. then when we do this multiplication, 1, 0, 0 times xyz is going to give us x, 0, 1, 0 times xyz is going to give us y, and the third one is going to be z. And then we have some just numbers we don't really know here, because we don't really know what these entries over here are. So if we look at this, every single possible x is going to be defined by only one possible b vector. So in other words, every single b vector corresponds to a unique x, because if x changes, right, then the b vector will change. So this means that there will only be one unique x for every b vector. So this is another way of seeing that this transformation will be one-to-one, because that is a definition of it being one-to-one. You need to have a unique b vector. You need to have at most one solution for x for every possible b vector that you can obtain through the transformation. So because of that, we know that this is a one-to-one transformation, so our answer is B for 4. Okay, in this question we have which of the following statements must be true. So we have this function, this transformation that's defined by 2x plus 1, and we're asked to see if it's a linear transformation. So just as a reminder, one of the properties of a linear transformation is that if you have transformation of two vectors that are in the vector space, then that should give you the transformation of u plus the transformation of v. Okay, so in this case, let's try that. This is just for addition. If it's closed under addition, it is a linear transformation. So t of u plus v is equal to 2 times u plus v plus 1. And we're like, is that equal to t of u plus t of v? Okay. Okay. That's supposed to be a question mark. That doesn't look right. Okay. So t of u is 2u plus 1, and then t of v is 2v plus 1. Hopefully you can see that this is definitely not equal to this. So because of that, this transformation is not closed under addition, so this is not true. It's not linear. The set of points x, y, z satisfying the equation x plus 3y plus 2z equals 13 is a subspace of R3. So a condition for a subspace is it must contain the 0 vector. Okay. Does this contain the 0 vector? If x is equal to 0, y is equal to 0, z is equal to 0, does that still equal 13? No, it doesn't. So because of that, it's not a subspace, because a subspace must contain the 0 vector. 3. The set 1, 1, 0, 0, 1, 1, 1, 1, 1 is a basis for R to the 3. Basis means we need to test if this is a linearly independent set. First of all, we need to see that it has dimension of 3, because a basis is the least number of vectors that are linearly independent that can span R to the 3. So first of all, there are 3 vectors. That's good. It could be a basis. Second test is to see if it's linearly independent. So I guess with this one, it's, I don't know, I think you could just do some basic row manipulation in your head. If we subtract this one from this one, we get 0, 0, 1, 1, 1, 0, 0, 1, 1. And from that, hopefully you can see that these are going to be linearly independent vectors, because none of them are multiples of each other, and they can't really be written as linear combinations. You could go a step further and do this row minus this row, or this vector minus that vector, and that gives you 0, and then this vector minus this vector, which gives you 0. So now these are definitely linearly independent linearly independent vectors. So whatever way you prefer, you will see that these are linearly independent because they cannot be written as linear combinations of each other. So this is a true statement. This is a basis. For the function R3 to R3 is defined by this transformation here, and this is a linear transformation. Okay, so just to confirm that is a linear transformation, we need to confirm that transformation of x1 plus x2, y1 plus y2, z1 plus z2 is equal to the transformation of x1, y1, z1 plus the transformation of x2, y2, z2. hopefully from this, we plug that in to this transformation expression, and that gives us x1 plus x2 plus y1 plus y2, x1 plus x1 plus x2 minus y1 minus y2, and then z1 plus z2. And this transformation gives us x1 plus y1, x2 minus y2, and then z1. Wait, I'm sorry, I don't know why I started writing 2's. Okay, x1 minus y1. And this one is x2 plus y2, x2 minus y2, and then z2. From addition, these two are the same, so this is going to be a linear transformation. It's closed under scalar, it's closed under addition. The other test you could do is closed under scalar multiplication. That's just saying is c times xyz equal to c times t of transformation of xyz. And there's nothing weird going on here, so hopefully you can confirm that this is the case. If that was illegible. Okay, so I mean, I guess we could do it, but c times x plus y. This gives us c times x plus y, c times x minus y, c times z equals c times x plus y, x minus y, z. So these are definitely equal, so this is a linear transformation. So our answer is going to be D. Okay, 6 let A be this matrix here, and its inverse is going to be defined by these terms B, I, J, where I is the row and then J is the column. So we want to find B1, 2. So you want to find A inverse at the entry on the first row and second column. So we kind of remember Cramer's rule, right? So, well, hopefully you remember Cramer's rule because it will potentially be tested. I don't know. Cramer's rule states that A inverse Ij is equal to 1 over the determinant of A times -1 times I plus j, and then the determinant of A, J, I, where this is the matrix when you delete the jth row and then the ith column. Okay, so let's start so first we want A inverse at 1, 2. So you need to find a determinant of A times -1 times 1 plus 2 times the determinant of A when we delete the second row. We delete the second row and the first column. So in this case, right, our Aij or AJI is going to be 2, 1. So the second row, delete it. First column, delete it. So we have now 0, -2, -3, 4. And this is, again, the symbol for determinant. So we're going to find the determinant of this. We need the determinant of A, so let's do that first. I'm going to expand along, I guess, this top row. It's the easiest because we have a 0, so that means for one of them we can just not compute it. So we take the determinant by, remember, first taking this entry, deleting the row and column that it's in, and then find the determinant of the remaining matrix. Okay, and then we do the 0, which just gives us 0, because it should be 0 times whatever. And then plus -2, delete the row column it's in, -3, 1, 2, -3. Okay, so that's going to be 4 minus -12 plus -2 times 9 minus 2, 16 minus 14, just 2. Okay, so we found the determinant of A is 2, and so this gives us 1 over 2 times -1 times the determinant here is going to be 0 minus 6, so we're going to have 3 as our result, so our answer is B. Okay, 7. So we have this linear transformation whose standard matrix is this. So standard matrix, what does that mean? So we have our transformation AX equals B. Okay, so A is going to be our standard matrix. Okay. Find all values of T such that that L is 1 to 1. 1 to 1 means that the columns of our standard matrix are linearly independent. And this means that we should look at values where this might not be the case. So let's see, we have T minus 2, negative 1, 2T plus 6, T plus 3. So one way to do this is you could just start row reduction. So we could do set row 2 equal to row 2 minus 2 row 1. And this gives us T minus 2, negative 1, 10, T plus 5. Do divided by 10, so let's do row 2 equals row 2 over 10. 1, T plus 5 over 10, T minus 2, negative 1. And then let's just, take the first row and subtract T minus 2 times the second row. Right, so that will just give us 0, negative 1 minus T minus 2 times T plus 5 over 10. And then on the bottom row we have 0, 1, and then T plus 5 over 10. Okay, and then now we kind of look at these two rows, and we ask ourselves, for what value of T is it linearly independent? Or, sorry, not linearly independent. For what, wait, actually, no, yeah. So, for what values of T are these two columns going to be linearly independent? So at this point, you can just start, plugging numbers in to conserve time. So, for example, like let's plug in T equals 0, just to see what that does. That gives you, let's make this clear. 0, 1, and then negative 1 minus, so T equals 0, so that's negative 1, and then 1/2. So negative 1 plus 1 is just 0. So you can see that these two columns are going to be linearly dependent. So this will not give you a 1-to-1 transformation because you need the columns to be linearly independent. So this means that this is definitely a condition that you need to have such that L is 1 to 1. So you can automatically just know that this is the answer. Yes, you can solve this, figure out what values of T make these two columns be linearly independent. But, perhaps an easier way to approach this would have just been to start plugging in these numbers from the start. So we knew like this matrix A was T minus 2, negative 1, 2T plus 6, and T plus 3. So if we had plugged in, say T equals 0, we would have gotten that negative 2, negative 1. Let me just do this so it's clear. If we had just plugged in T equals 0, we'd have gotten negative 2, negative 1, 6, 3. Clearly, these two columns are linearly dependent, so we would automatically know much more quickly that L needs to be not equal to, or T needs to be not equal to 0 for L to be 1 to 1. So this is just another way of doing it that's much faster, and also because you have the advantage of it being multiple choice. But in other cases, you would need to do this kind of row reduction and get to some point where you can establish the pivot columns, or the pivot entries in the matrix. So that's problem 7. Okay, so which of the following sets of vectors are linearly dependent? So first of all, maybe an easier one to look at is, this one. Obviously, this one is not a multiple of this one, so there's only 2. So if they were dependent, they would have to be multiples of each other. That is definitely not the case, because if you do 1/3 and then 1/3, 1/3 of 4 is not 2, so you wouldn't be able to make these the multiples of each other anyways. So this is going to be not linearly dependent. Same thing here, if we try to make these a multiple of each other, you literally cannot. this is multiplied by 3, multiplied by 3, this will need to be 12 for this to be a multiple of this vector. So definitely not dependent. They're not multiples of each other. They cannot be written as linear combinations of each other. This one, part number A, A, you have, t squared, then you have t cubed, and then you have 4t as like the highest degree, I think it's called, of the expressions. So you wouldn't be able to write them as linear combinations of each other because they're all different degrees. So you can't write this expression in terms of these two because there's nothing to cancel out the t cubed or the 4t. So this is not linearly dependent. Then also, you can see that this is the same argument. The degree is different, and they're definitely not multiples of each other. And so you can see that this is not dependent as well. So this must be linearly dependent. You can confirm this by, row reducing it. So remember our favorite tests for linear independence, right? So if you have 3 vectors and you want to make sure that these vectors are linearly independent, then you would write this expression here where c1, c2, c3 are scalars, and v1, v2, and v3 would be linearly independent if the only solution for this is c1, c2, c3 equals 0. So you could put it, in this form 3, 2, 1, 5, 2, 1, -1, -2, -1 equal to 0, and then row reduce. And ultimately what you should get is that this will give you a row of zeros. So I guess we could actually do that just as an exercise. So, well, actually we don't need to do much because you can already see that this row and this row are multiples of each other, right? So if we just did row 2 equals row 2 minus 2 row 1, we would get this row of zeros. And this row of zeros should signify to you that there will be more than one solution for c1, c2, c3 that gives you this expression. So because of that, it is linearly dependent. So the answer is D. Okay, so to find the transformation here, where you're transforming this kind of polynomial into something like this. So the kernel of this transformation has a basis of what? So what does kernel of t mean? So this means this is a set of vectors. In this case, these vectors would be a0 plus a1t plus a2t squared. So it would be determined by a1, a2, a3 that map u to 0. So it's kind of like the null space, or it basically is a null space. So basically, we want to find when this transformation maps to 0. So when this equals 0. And this will always map to 0 when a2 equals 0. So this means that our a0 plus a1t plus a2t squared, which is our input vector, becomes, for a2 is equal to 0, it becomes a0 plus a1t. Our basis for the null space of this transformation is going to correspond to the spanning vectors. So this corresponds again to the free variables. So in this case, notice our free variables are going to be, a0 times 1 plus a1 times t. So 1 and t are these spanning vectors that will span the solution set for this transformation to 0. So because of that, we consider the answer is C. So just to recap, the basis for this null space, so this transformation from this to 0, is going to be described by this solution, because we're constrained here to have a2 equal to 0 for this transformation to map to 0. But a0 plus a1t, that could be anything. a0 and a1 can be anything. So that means that our basis that describes these spanning vectors is going to be 1 and t. Okay. Let A be this interesting matrix, and we denote little a as the determinant of 2a, and then b as the determinant of a squared. So we're trying to find what a plus b are equal to. Okay. These are just applying the rules of determinants. So the determinant of 2a is going to be 2 to the n. So n is the dimension of a. So the dimension of a here is going to be 4. It's a 4 by 4 matrix. Times the determinant of a, which is equal to 16 times the determinant of a. And the determinant of a, let's just do that. So the determinant of a, let's expand along this row or column. So we have the determinant of a equals, so these 0 entries just mean that I don't have anything to do with them, because, 0 times whatever is going to be 0. Then remember we apply this checkerboard pattern. So, oopsies, that's not right. Okay, so we apply this checkerboard pattern. We have a plus here, which corresponds to this plus here, so we'd have +1 times deleting the row and column that this entry is in. So the determinant of 1, 2, 2, 0, 1, 2, 0, 0, 2. So notice this is like a upward triangular matrix. I don't really know the formal name for it, but a property of this is that a determinant of this kind of matrix where you have, this upper triangle or even lower triangle, for example, of numbers, and then the opposite triangle, it has all zeros. The determinant of something like that is just going to be the elements on the diagonal multiplied with each other. So that just gives us a determinant of a is equal to 2. So we plug that into this 16 times the determinant of a, and we get that it's equal to 32. Okay, so now we need to find the determinant of a squared. So what is that equal to? This is the determinant of a times a. And then that can be decomposed just by determinant rules into determinant of a times determinant of a. And that gives us 2 times 2, which is 4. So a plus b is equal to 32 plus 4, which is 36. Okay, in this problem we have this matrix A, and we're trying to figure out which of the following is always true. So the first option is a null space of A is a subspace of R to the 3. Remember that the null space of A is the space that is spanned by these spanning vectors when you solve the equation AX equals 0. Okay, and so what we want to do then is to figure out what these spanning vectors are and to evaluate if they satisfy the requirements for a subspace. So the way we do that that is simply with row reduction. So we write out our augmented matrix like this, and then we just row reduce to see what the spanning vectors will be. Okay, so one way to do this, I'll just do row 1 or row 2 equals row 2 plus row 3. I'm just going to add row 2 and row 3 together. This gives me 0, 0, 10, 5, 0. And then I'll keep the first row as is. And then I'm just going to add, so after I do this, I'm going to add 2 times row 1 to row 2. Row 3. And that'll give me 0, -1, 7, minus 2 is 5, -4, and 0. Okay, so now I'm going to just divide the second row by 5, so 0, 0, or I'll just divide by 10, so we have this. And then the first row I'll keep the same, and then this one I'll just divide by -1, so okay. And so hopefully you can see that. Okay, I'm gonna actually swap the last 2 rows just so it's clear. It's more clear. Okay, so hopefully you can see that there's a pivot column or pivot entry in each row. So this means that there is only one free variable, which is going to be described by this vector here. Or not exactly this vector. It will be described once you get this in row reduced echelon form, so you make these entries 0. But just, I think from this point, you can see that, okay, yeah. So just from this point, though, you can see that there will only be one spanning vector. So we know that there's one free variable, and I mean, what you could do after this is you can row reduce this further and put it in row reduced echelon form. So, you could add 5 times row 3 to row 2, and then add row 3 to row 1. If I do that quickly, that gives you like 4 plus 5 halves, and then like -2 plus 1 half. Okay, so like this would be, one form of your spanning vector. And so you can see there's only one spanning vector, and furthermore, this spanning vector does not contain 0. So you have this singular vector. If we actually did solve for x here, we would move everything over to the other side, and we would get 2 minus 1 half, -4 minus 5 halves, -1 half, times some our free variable, which we designated t. And so this is your spanning vector, right? And clearly this does not include the 0 vector, which is one of the requirements of a subspace. So your subspace must contain the 0 vector, and this does not. So like your subspace would literally be described by just this vector, and that's not sufficient for the null space to be considered a subspace. So this is not true because it does not contain a 0 vector. Okay. In part B, the dimension of the null space of A is 1. So we actually kind of just figured that out because we only have one spanning vector. So the null space of A is spanned by this vector. There's only one vector in the basis, so the dimension of the null space is 1. So this is true. The column space of A is the subspace of R, so 2. So the column space of A is the span of the vectors of A. And you can see that the vectors of A have 3 elements in them, right? 1, 2, 3. This doesn't make sense then for it to be a subspace of R to the 2 because it has 3 elements and the spaces themselves are different. And so you cannot argue that this is a subspace of a different dimension space. So this is false. The equation of Ax equals 0 has a unique solution. We also kind of just did this because we did literally solve for this equation right here. And we found that we can write our solutions as this form where t could be anything. So obviously there's not a unique solution because if there was a unique solution, then x would have to be, one specific vector. But this could be any vector because we have this free variable. So because we have a free variable, there's not a unique solution. So this is false. The rank of the matrix A is 4. So this just doesn't make sense because rank is the number of non-zero rows in row reduced echelon form. And we kind of put it in row reduced echelon form here. And you can see that first of all there's only 3 rows, so you cannot have a rank of 4 if you only have 3 rows. So already this is false, but also there's 3 non-zero rows. So that's another way of saying that this is not true. So the answer is B. Okay, so in 12 we have which of the following are subspaces of P? 3, which is the vector space of polynomials of a degree at most 3. What does this mean? This means that our vector space, a vector in P3 would have the form of something like ax cubed plus bx squared plus cx plus d. And which of the following are subspaces? In A, we have the set of all polynomials of the form at plus t squared plus a minus b times t cubed, where a and b are real numbers. So the requirements of a subspace, first one is that 0 is in the subspace, or in the vectors. In the vector space. So if 0 is in the space, then we're good. Then if we have 2, elements a and b that are in the vector space, then a plus b needs to be in the vector space as well. The other one is if we have a is in the vector space, then some scalar times a is also in the vector space. Okay, so checking these conditions with all of these, we first look at the a and we need to check is a equals b equals 0, which means that 0 is in the vector space in this set. So if a equals b equals 0, we have t squared as a result. So t squared is not equal to 0, and so that means that we are not able to have the 0 polynomial in this set. And that means that this is not a subspace because it does not contain the 0 polynomial. So this is not true. Ooh. This is not true. In part B, we have a set of all polynomials pt with p1 equals 1. So first of all, if p1 equals 1, then looking at this just generic expression for any polynomial in this p3 vector space, let's do this, then these polynomials have to satisfy the constraint that a plus b plus c plus d equals 1. And this is just plugging in 1 into this px here. I don't know why I wrote a 1 there. It should be x. So p of x, p of 1, plugging in 1, a plus b plus c plus d is what you get. And the constraint here is that p of 1 equals 1. So if we look at this expression, again, we do our first test, which is it possible to have a, b, c, d equals 0? Well, in this case, if a plus b plus c plus d equals 0, then you get 0 equals 1, which does not make sense. So that means that this is not a subspace because it does not contain the 0 polynomial. And so the third one is, oh, sorry, I think I kind of misspoke with this one. So not that there's no 0 polynomial in here, but there's no condition that is satisfied by just the polynomial equaling 0. So if this is just equal to 0, this will not satisfy this condition here. And so because of that, this is not a subspace. Okay, in part C, we have the set of all polynomials with p negative 1 times p negative 2 equals 0. Looking at this part, what is our constraint? So our constraint is when we have p negative 1, so we plug in negative 1 here for x. So that gives us negative a plus b minus c plus d equals 0. Or we could have p negative 2 equaling 0. And so plug it, sorry. Okay, so plugging in, sorry, I don't know why I sound like I'm chewing gravel today, but we plug in x equals negative 2, so we get negative 8x plus 4, wait, what am I doing? Negative 8a plus 4b minus 2c plus d equals 0, right? Because either p1 negative 1 equals 0 or p negative 2 equals 0, or they both equal 0 to satisfy their multiplication equaling 0. Okay, so these are our constraints, right? So first thing we can check, is it closed under, does it contain 0? So if a, b, c, d equals 0, you can see that these two expressions will equal 0. So this satisfies the constraint. So 0 is in this set of polynomials. So we can have checked the first one. Second one, if a, b is in this set, then a plus b is in this set as well. So we have, let's see, let's just say we have this first polynomial, which is denoted by a1 x cubed plus b1 x squared plus c1 x plus d1. Then p2 equals a2 x cubed plus b2 x squared plus c2 x plus d2. And then, okay, so let's say that these two polynomials are both in this set. So p1 negative 1 times p1 negative 2 equals 0, and p2 negative 1 times p2 negative 2 is equal to 0. And let's say they satisfy these in different ways. So let's say p1 satisfies it because, you know, from these conditions here, negative a1 plus b1 minus c1 plus d1 equals 0. And let's say for p2 it satisfies it because negative 8 a2 plus 4 b2 minus 2 c2 plus d2 equals 0. So these polynomials are in the set, but they satisfy this constraint differently. Okay, now we need to check if p1 plus p2 is in the set. Okay, so p1 plus p2 gives me a1 plus a2 x cubed plus b1 plus b2 x squared plus c1 plus c2 x plus d1 plus d2. And so okay, yeah. So then we want to check our constraint. So we want to check that p-1 times p-2 is equal to 0. So to check that, we need to see here is a1 plus a2. Okay, this is going to be kind of annoying. So what we're going to do, I'm going to call this just pt, so p total. So we're trying to check if p total -1 times p total -2 is equal to 0. Right? So the way we do that is we literally plug this into the expression. So we get -a1 plus a2 plus b1 plus b2 minus c1 plus c2 plus d1 plus d2. This is pt -1. Then I'm going to do pt -2. And that's going to give us -8 times a1 plus a2 plus 4 times b1 plus b2 minus 2 times c1 plus c2 plus d1 plus d2. See if this is equal to 0. Or sorry, not if it's equal to 0. Oh yeah, it is equal to 0 if it is. Okay, so we're just trying to test if this expression is actually equal to 0, so if it satisfies the constraint of this set. Because we need to check if a and b are in the set if a plus b is also in the set. Okay, so here's the caveat, I guess, of this part. So like, remember at the beginning we said that p1 and p2 satisfy these constraints differently. So there is a chance, that it would satisfy them, that both satisfy them via the same condition. Like if this is condition 1, this is condition 2. It's possible that p1 and p2 satisfy the first constraint. However, what about the case where they only satisfy one of each constraint? So in this case, this satisfies the first constraint, but p2 only satisfies the second constraint. Well, in that case, if you plug these conditions into these expressions, first of all, even though -a plus b1 minus c1 plus d1 equals 0, it doesn't mean that -a2 plus b2 minus c2 plus d2 is equal to 0. So this could be non-zero. This term could be non-zero. Same thing over here. So if we plug in the condition 2, -8a2 plus 4b2 plus minus 2c2 plus d2, that could be 0, but it doesn't mean that -8a1 plus 4b1 plus minus 2c1 plus d1 is equal to 0. So because of that, you could actually end up with two non-zero terms here, so then it would not be equal to 0. So this condition that, if you have two elements of the subset, that the addition of the two are also in the subset, this is not necessarily true for all conditions and all possible polynomials in the set. So because of that, this is not closed under addition. So because of that, we can say that this is not a subspace because it's not closed under addition. And like just to recap, I guess another way to think of this is kind of a nonlinear term, so you should already be suspicious of if it's closed under addition. But you can prove it, more formally here, where you can see that two polynomials that are in the set but satisfy different constraints for the set could have an addition that does not satisfy the constraint. And how that happens again, I'm just going to recap because it could be confusing, is that we created these two polynomials just arbitrarily, but we just said that one satisfies this constraint, the other one satisfies this constraint. And then we're checking, okay, if p1 plus p2, does this satisfy this constraint here? And so we did that. We found this pt, we added them together, and we plugged it into this constraint here. And then we plugged these individual constraints into this overall equation here from pt minus 1 times pt negative 2 equals 0. And we found that, even though a1 plus b1 minus c1 plus d1 could be 0, it doesn't necessarily mean that these terms add up to be 0. And the same thing in the second term. So you could have, these terms being equal to 0, but it doesn't mean that these terms add up to be 0 too, because the only constraint we know about that is from this initial statement that we made. So because of that, we could have two non-zero terms, and that means that they multiply together to be potentially non-zero, or most likely non-zero. And so that means that this is not satisfied for all possible polynomials in the set. So if it's not satisfied for all of them, then it's not closed under addition, so it's not true. So it's not a subspace. So that's how we know that from C that this is not a subspace. Okay, in part D, we have a set of polynomials pt with p naught or p0 equals 0 and p2 equals 0. So basically here you have okay, so first of all, let's just see p0 equals 0. We plug that into this constraint here. P0 equals a, okay, well, a plus b plus c gets deleted because x is equal to 0. And then we have d. So that means d is equal to 0 because we know that p0 is equal to 0. Okay, so our first constraint is that d is equal to 0. And then for p2, we have is equal to 8a plus 4b plus 8a plus 4b plus 2c. And then we know that d has to be 0, so we can just ignore the d, and then we have this equals 0. Okay, so the first question is a 0 polynomial in here? So this condition here. If a, b, c, and d is already equal to 0, but if a, b, c is equal to 0, then this condition is still satisfied, so the 0 polynomial is in here. So that means that condition 1 is satisfied. Second condition. So if we have two polynomials where p naught, why do I see, I keep saying p naught, it's p of 0. So looking at the second requirement for a subspace, you know that we can say we have two polynomials p1 equals a1 x cubed plus b1 x squared plus c1x. Again, for it to be in the subspace, we need to have d equals 0, so we can just ignore the d term. And then we have another polynomial, say, where a2 x cubed plus b2 x squared plus c2x. This is really fun. And then we add them together, and then we do a1 plus a2 x squared cubed plus b1 plus b2 x squared plus c1 plus c2 x. Okay. Okay, so we know that p1, p2, we've defined them such that they're in this set. So they satisfy p0 equals 0 and p2 equals 0. So the constraint for that means that, so let me write this over here. I'm running out of room. Okay, so the constraint for that means that a1 plus 4b1 plus 2c1 equals 0. And then for p2, the constraint is that a2 plus 4b2 plus 2c2 equals 0. This is because it needs to satisfy both this and this. So we have these constraints, and now we're checking if pt also satisfies these constraints. So is p0 equals 0? Yes. If we plug in x equals 0 here, we get 0. The second constraint is pt of 2 equal to 0. That just gives us 8a1 plus a2 plus 4 times b1 plus b2 plus 2 times c1 plus c2. Okay, so because of these constraints, we know that a1 plus 4b1 plus 2c1 is 0 from here. Then we also know that a2 plus 4b2 plus 2c2 is equal to 0. So both of these equal to 0, so this is going to be equal to 0 because of these constraints right here. So because of that, we can say that this is closed under addition because when we add these two polynomials that are already in the set, they give a polynomial that is also going to be in the set because it satisfies these conditions. So it is closed under addition, so that's good. The third one is that closed under scalar multiplication. So this one kind of quick. So we know from, let's just take p1 here because I don't want to rewrite everything. So p1, we know that the condition is a1 plus 4b1 plus 2c1 equals 0. It's already in the set. Then what happens if we do, let me just make this f, some scalar times p1. That gives me f(a1) x cubed plus fb1 x squared plus f c1 x. Okay, so does this satisfy, let's call this, okay, never mind. So does this satisfy these constraints here where p0 equals 0 and p2 equals 0? So if p0 equals 0, we plug in x equals 0. This does give us 0, so we can confirm that this first condition is satisfied. Is this polynomial
where we plug in x equals 2 equal to 0. Well, then we just have 8a1 plus 4b1 plus 2c1 all times f, because I just factored that out. Is this equal to 0? Yes, because we know that this is going to be equal to 0, because we had this initial constraint for p1. Why do we have this constraint? We have this constraint because we said that p1 is going to be already in the set of these polynomials. So that's like the key part of all of these steps. We have to choose two polynomials, or choose a polynomial that's already in the set, and define the constraint that is associated with it because it's in the set. So we know that this is going to be equal to 0 because of this constraint here. So it is closed under scalar multiplication too, so this is equal to 0. Yeah, so we know this is closed under scalar multiplication, addition, and it has a 0 vector, so D is the answer. For part E, I'm not going to go through all of these things again. Hopefully you can check yourself. But right, if first of all, integer coefficients A, B, C, D here can be 0, and those are still integers, so it is satisfied. For 2, if you add 2 integers, they're still integers, so this is going to be closed under addition. But E is, or 3, the third condition is the kicker, because if you have, some scalar times some polynomial, your scalar could be like a decimal. It doesn't have to be an integer. So if you had like times pi, then obviously your coefficients are not going to be integers anymore. So it's not closed under scalar multiplication, so this is not true. So it's not going to be a subspace. So our answer is D. Okay. Okay, in this problem we have A is some square matrix, and we're trying to find if this vector 3i minus 1, 2 is an eigenvector. And well, we know it's going to be an eigenvector, but we're trying to figure out which eigenvalue it corresponds to. So how do we find the eigenvalues? So first of all, the determinant of A minus lambda I, where I is an identity matrix, and we set that equal to 0. And then we solve for lambda, and that's how we get the eigenvalues. Okay, so we plug in that into A, so -1 minus lambda, -5, 2, 1 minus lambda. That gives me -1 minus lambda times 1 minus lambda plus 10. Okay, and that gives me lambda squared plus 1 minus 1 lambda, so 0 lambda, minus 1 plus 10, which is plus 9, equals 0. So from this, lambda has to be plus or minus 3i. Okay, so that already eliminates these 3 answer choices, and we get, okay, yeah, so now we just need to figure out which eigenvalue this corresponds to. So now we have to find the eigenvector. So how to find the eigenvector? We plug in A minus lambda I. So we plug in for each lambda into this expression, and then we try to solve for an x that satisfies this expression. So let's do that with the first one. So lambda equals 3i. That gives us A minus 3i times the identity matrix is just -1 minus 3i, -5, 2, 1 minus 3i, and this is equal to 0. Okay, so what you can do is you can multiply by the, what is the term? Complex conjugate, I think. So what you do is you can do row 1 equals row 1 times 1, -1, -1 plus 3i. Okay, so what does that give you, right? Complex conjugate, that's when you just multiply by this, right? So we have, let's see, we have 1, why can't I do math? -3i plus 3i 0, yeah, so plus 10. Wait, what am I doing? Okay, -3i times 3i is going to be plus 9. Okay, then we have -5 times -1 plus 3i. Okay, and then this is going to be 1 minus 3i. So this just becomes 10. Right, and then hopefully you can see that if we divide the first row by 5, we get the second row. So really we just need to pick some x that can satisfy the expression. Maybe I'll just write it out. Okay, so we can see that if we divide this row by 5, we get this row. So we can just eliminate that row entirely because it's just a multiple of the other row. So we have 2, 1 minus 3i. Okay, so recall that we need to find some x. So for some, we need to find some x that satisfies this expression here, where we have 2x plus 1 minus 3i times y equals 0, where, you know, our x vector is xy. So I guess one of the options would be to do, for here, we can just look at this expression, to be honest, and kind of cheat a little bit with that. So if we have x of 3i minus 1, then we get 2 times 3i minus 1 plus 1 minus 3i times 2. And just from algebra, you can see that this equals 0. So that actually does satisfy this expression. So an x could be 3i minus 1 and 2. So that means that our eigenvector corresponds to 3i. So our answer is C. Okay, so 14. Suppose that A is a 3 by 3 real matrix having distinct eigenvalues, lambda 1, lambda 2, lambda 3, which of the following statements are true. Okay, so part 1 says that A is diagonalizable. This is true. So this is just a property of diagonalizable. Well, one condition for diagonalizable matrices. Like if you have distinct eigenvalues, then you are definitely going to have a diagonalizable matrix. This is just kind of a definition. I think this is proved somewhere. I don't know if I've already proved this somewhere, but it definitely exists. So I'm just not going to go into it right now. And I think you would find this online as well. And the second part is if v1, v2, v3 are eigenvalues for eigenvectors for lambda 1, lambda 2, lambda 3, then v1, v2, v3 is an orthogonal set. Our orthogonal set, right, means that you have, you know, your eigenvectors would satisfy v1 dot v2 equals 0, v2 dot v3 equals 0, v1 dot v3 equals 0. That's what it means for them to be an orthogonal set. But from doing a lot of eigenvector problems, I think that maybe you have come across instances where they're not necessarily going to be orthogonal. There's not really any indication. They just have to be linearly independent, but they don't have to be orthogonal. So they don't have to be at 90 degrees of each other. Yes, I just pulled up an example here where you I think this is the spring 2023 midterm 2 exam 2. And this is an example where we had to find the eigenvalues and eigenvectors. From these eigenvectors here, you can see that, this dotted with this is not equal to 0. Neither is, I guess these two are, but that's irrelevant because if we dot these two together, they're not orthogonal. And the same thing if we dotted these two together, not orthogonal. So it doesn't mean that the eigenvectors don't necessarily have to be orthogonal with one another to be eigenvectors. And so that means that our our eigenvectors do not necessarily have to be orthogonal. So this is not true. Just to reiterate, because I'm not sure if that was clear, basically eigenvectors have to be linearly independent, but it doesn't mean that they have to be orthogonal. And that example that we just saw, we had 3 distinct, linearly independent eigenvectors, but they were not orthogonal to each other. So not all of them were orthogonal to the other ones. So because of that, it's like a counterexample to show that they don't have to be orthogonal to be eigenvectors. All right, in 3 we have if v1, v2, v3 are eigenvectors, then the matrix is invertible. This is going to be true based on the definition of invertible matrices. So we know that the eigenvectors have to be linearly independent. So that by definition just means that you're going to have linearly independent columns in this matrix, right? The columns are going to be linearly independent. That means that this matrix will be invertible just by definition of invertible matrices. So this is true. And 4 we have the determinant of A is equal to lambda 1 times lambda 2 and lambda 3. Okay, so I guess one way to think of this is we already know that. Wait, I don't know why I slashed this one through because this one is true. Okay, so 1 is true. Let's just take a moment to delete some of these options. So this one's obviously not right. This one is also not right. This one is also not right because we eliminated 2. Okay, sorry. Back to 4. So is a determinant equal to this? So we already know that A is diagonalizable, right? Because we said that this is true. And we argue that this is true just because there are distinct eigenvalues. So if we have the determinant of A equals this, we know that A, because it's diagonalizable, can be written as P times D times P inverse, right? Where D is a diagonal matrix composed of your eigenvalues. So lambda 1, lambda 2, lambda 3, 0, 0, 0. And then P is like your, it's composed of the corresponding eigenvectors. So it's, okay, that's not P inverse. So P is equal to this, right? So in short, we can take the determinant of both sides. We get determinant of A equals the determinant of P times the determinant of D times the determinant of P inverse. Okay, determinant properties, determinant of P times determinant of P inverse just becomes 1. Okay, so that means the determinant of A is the determinant of D. Determinant of D is going to be lambda 1 times lambda 2 times lambda 3 because it's a diagonal matrix. Because of that, yeah, so then the determinant of A will literally be lambda 1 times lambda 2 times lambda 3. So this is true. So our final answer is E.
In this problem, we have let the transformation from R2 to R2 be linear, such that the transformation of this vector gives us this, and this vector gives us negative 5, 3. Which of the following is a basis for R2 such that the matrix transformation relative to the basis B is diagonal? When you see diagonal matrix, the first thing you should think of is diagonalization. So we probably want to diagonalize the transformation matrix, which is initially written as negative 4, 2, negative 5, 3. Where the columns are composed of the transformed vectors when you're transforming the original basis. So in this case, our original basis is E1 and E2. So this is our original transformation matrix, and we want to diagonalize this because the eigenvectors will form the basis for a diagonal transformation matrix. So to diagonalize this, we do our favorite determinant of, in this case, T minus lambda I. Okay, I'm actually going to call this A because T is kind of symbolizing the transformation and not the matrix itself. So the matrix that is causing the transformation is this AX, right? Equals B. So to find the eigenvalues, we do the determinant of A minus lambda I set equal to 0 and solve for lambda. This means we have negative 4 minus lambda, negative 5, 2, 3 minus lambda equals lambda squared plus lambda minus 12, so minus 2 equals 0. So that means lambda equals 2 and 1. Wait. Negative 2 and 1. Now we can solve for the eigenvectors of, the eigenvectors for each eigenvalue. So for eigenvalue of negative 2, we have, the way we solve for eigenvectors again is to solve this equation for x and just plug in our lambda. So we have A minus lambda I, in this case is going to be negative 2, negative 5, 2, 5. And this gives us, you can see that these two rows are linearly dependent, so we can automatically just guess or pick an eigenvector that satisfies this condition where you have 2x plus 5y equals 0. So I'm just going to guess 5 and negative 2. Then we do the same thing for lambda equals 1, where we end up with negative 5, 2, 2. And then we can pick another eigenvector where x2 is going to be, let's just say 1, negative 1. Yeah. Okay, so now we have these two eigenvectors, and this is actually going to compose, these two vectors are actually going to be our basis for the transformation that has a diagonal matrix. So because of that, we can look at our answer choices. It's not this one. This is not right. And I think it's B. Yeah. So our answer is B. And just to reiterate, the actual transformation matrix that's associated with these two basis vectors is going to be given by the eigenvalues that we obtained. So it'll be negative 2, 0, 0, 1. that would actually be our transformation matrix relative to the B basis. But our B basis is going to be composed of our eigenvectors because that's going to give us a diagonal matrix for the transformation. So our answer is B.
In 16, we have let this xy be a particular solution to the differential equation here, satisfy the initial conditions of this. Then x2, y2 is what? Okay, so this is just a standard differential equation problem. So the way we do this is we solve for the eigenvalues and then eigenvectors of the system. So we have, I'm just going to call this matrix A. So A is going to be, this thing right here. And we find the eigenvalues by doing the determinant of A minus lambda I, set that equal to 0. That gives me determinant 2 minus lambda, -2, -5, -1 minus lambda. Okay, so that equals 2 minus lambda, -1 minus lambda, minus 10 equals lambda squared. -2 plus 3 lambda, minus 2 minus 10, so minus 12 equals 0. Did I do that right? Wait. Oh, sorry. This should be minus lambda. Okay, and when we factor this out, we get lambda minus 4 times lambda plus 3 equals 0. Okay, so we know that our eigenvalues are 4 and -3. Okay, now to figure out eigenvectors, we plug in our eigenvalues into the expression a minus lambda I times x equals 0. We solve for x. Okay, so now we have a minus 4i, so that's -2, -2, -5, -5, equals 0, 0. You can see that these are linear, or they're multiples of each other, and so we can let's just delete that. So we know that the expression for x must satisfy -2 x minus 2y equals 0. So we can just, arbitrarily pick, let's just have our first eigenvector be 1 and -1. Okay, we do the same thing for -3. When I do that, we get 2 minus -3, 5, -2, -5, 2. Okay, once again, these are multiples of each other, so I'm just going to ignore this row because it can be reduced to 0. So it needs to satisfy the expression 5x minus 2y equals 0. So our second eigenvector is going to be 2, 5. Let's see. Just to recap, you can literally pick anything else for your eigenvectors. It does not matter because anything will get absorbed into some constant out front, which is then going to be determined by your initial conditions. So just so what I think it's more clear if I write out the expression that we get. So our expression then for x of t and y of t is going to be e to the lambda t. So first our thing is e to the 4t times the corresponding eigenvector, which is 1, -1, times some constant, plus c2 times e to the -3t times 2, 5. So what I was saying earlier about the eigenvectors can be anything that satisfies this expression. It doesn't have to be these, for example, because anything multiplied by it will just be absorbed into this constant out here. So I just chose this, but it doesn't really matter. Okay, so now we have our expression for x, t, and y, t, and we need to find the what c1 and c2 are, so we can plug in our initial conditions, which are given here. That gives us x of 0 is equal to 5, so plugging in t equals 0, we get, let's see, ICs. We got c1 plus 2c2 equals 5, negative c1 plus 5c2 equals 5. Okay, so we can solve for this. We can add this together. 10, 7c2 equals that. Okay, that's not right. This is supposed to be 9. This is 14. Okay, so c2 is equal to 2. Okay, c2 is equal to 2. And that means c1 equals 1. Okay, so now we have, so now we can plug that into this expression here. And then we get x of t times y of t equals 1 times this and then 2 times that. Okay, so now what we can do is figure out what x2 and y2 are. So x2 is equal to 1 times e to the 8th. You plug in t equals 2, right? Times 1 plus 2 times e to the negative 6 times 2. And then y of 2 is going to be negative 1 times e to the 8th plus 2 times e to the negative 6 times 5. So that gives us these. So we add these two together, these two cancel, and here we get 14 e to the negative 6, which is A.
Okay, 17, assume all vectors and subspaces are in Rn, which of the following statements is false. A, the best approximation to y by elements of a subspace W is the vector y minus projection of y onto W. We probably want to draw pictures here because that will help us the most. So this plane, I'll just call it the subspace W. So let's say that y is something like this. It's kind of sticking out here. The projection of y onto the subspace is going to be this vector right here, where we have a 90-degree angle here. That's the projection of y onto W. They're saying that the best approximation to y is given by y minus the projection. So y minus the projection vector is just going to be this vector here. So let me draw it in blue. So this is going to be the y minus the projection of y onto W. That is actually the distance between the best approximation and the actual vector. So that distance is actually minimized when you are making the best approximation. But the best approximation is actually this vector right here. This vector is actually going to be the best approximation that you can get to y. The y minus projection of y onto W is just the distance between your approximation and the actual vector. So the best approximation of y would actually just be the projection of y onto the vector space W. So this is false. So this is a false statement, so that's going to be our answer. Let's look at the other problem options too. So we have z is orthogonal to u1 and u2. Then if W is a span of u1, u2, then z is in the subspace perpendicular to the W subspace. Okay, let's draw out our subspace. So let's imagine we have two vectors, u1, u2, and the span of them is going to be like the plane that they exist in, right? So this is W. And then z is orthogonal to them, so it's perpendicular to u1 and u2, so we have z here. So, well, okay, they don't have to be perpendicular. But z is perpendicular to u2, and it's also perpendicular to u1. Okay. Then z is in the subspace that is perpendicular to W. This is going to be true because it is perpendicular to both vectors that span the subspace W. So it's going to exist in the plane perpendicular to W, which is kind of like, I'm not very good at drawing, but kind of something like this. So z would be in the subspace perpendicular to W. So this is a true statement. Okay, we have y equals z1 plus z2, where z1 is the subspace W, and z2 is in the subspace perpendicular to W, or orthogonal to W. Then the projection of y onto W is z1. Okay, so let's imagine we have z1 and then z2, and they're living in different subspaces, so they're orthogonal to each other because of that. So now we have, so they're perpendicular because they're living in orthogonal subspaces. So then y is equal to z1 plus z2, so it's kind of something like this. This is y. And we're saying that the projection of y onto W is going to be z1. So this is going to be true because you can see the projection of y is going to be onto z1, and z1 is already in the subspace of W. So it's basically like a projection onto this z1 direction. So the projection is going to be equal to z1. So this is going to be true. If x is not in the subspace W, then x minus projection of x onto W is not 0. If we imagine our subspace here W, and then we have some x that's not in the subspace, like this, then the projection onto W is going to be something like this. So this here is a projection of x onto W, and this is x. So hopefully you can see that if it's not in the subspace, it will have some non-zero difference between the x and the projection, and that difference is shown here. If x was in the subspace, then it would literally be flat, on this plane, which I've drawn as a subspace. It would be flat on this plane, and so then then x minus the projection of x onto W would actually be 0, because there's no difference in distance between these two vectors. But because x is not in the subspace, it's going to be deviated slightly from this plane, so you will have a non-zero difference between your projection and the x vector. So this is a true statement. If the columns of n by n matrix A are orthonormal, then the linear mapping x to ax preserves lengths. This is a true statement. I think this problem was in, the final exam, fall 2022 final exam. If I go through it really quickly, you see that if we have orthonormal columns, we can write A as being, let's say, A1, A2, where these are the columns of A. And we know that they're orthonormal columns, so we know that A1 dot A2 equals 0. And because it's orthonormal, then the magnitude of the column vectors are going to be equal to 1. So that means that A1 dot A1 equals 0, and A2 dot A2 equals 0. So when we map from x to ax to check if length is preserved, we would want to check if x dot x equals ax dot ax. And to check this, we do some fancy manipulation where we have ax transpose times ax is equal to this. And we get x transpose times a transpose times ax. And that gives us, so to figure out what A transpose A is, we know that A is equal to this. So A transpose is equal to A1, A2. And then we have A1, A2. And so that actually gives us the matrix A1 dot A1, A1 dot A2, and then A2 dot A1, A2 dot A2. And so because we know that A1 dot A2 is 0 and A1 dot A1 and why did I put 0? These should be 1. It should be A1 dot A1 equals 1 and A2 dot A2 equals 1. We can plug that in here and we get 1, 0, 0, 1. So A transpose A is just the identity matrix. So that means that we end up with x transpose times identity matrix times x, which is just x transpose times x, which is equal to x dot x. So we essentially reduce this down to x dot x, so the length is preserved because that's equal to the original x dot x. So this is going to be a true statement. If you want to see this in more detail, I think it's problem 19. Yeah, it's problem 19 of fall 2022 final exam. So yeah, there's many variations of this statement in there, so I would encourage you to check that out if you're not familiar with how to do this kind of problem. So yeah, the answer for 17 is A. Alright, so here we have this real 2x2 matrix A has eigenvalue -2 plus I, and it has the corresponding eigenvector of V, which is a real solution to the system here. So our generic solution to any system like this, right, is e to the lambda t times the eigenvector that corresponds to it. So in this case, let's just have it be V, right? So the strategy here is to just convert everything into sines and cosines. So for example, here we have e to the -2 plus I times t times 3 minus I, and 4 plus 2i. Okay, so what we do here then is we get rid of, so we kind of split this up into -2t times e to the it times 3 minus I, 4 plus 2i. And so what happens then is we
factor that into the cosine t plus I sine t. So this becomes that. We still have our e to the negative 2t times 3 minus I, 4 plus 2I. And then when we factor that, or we expand that out, we get e to the negative 2t times 3 minus I times this expression, which gives us 3 cosine t minus I cosine t plus 3I cosine t plus sine t. Do the same thing on the bottom here. Cosine t plus I sine t times 4 plus 2I. That gives me 4 cosine t plus 2I cosine t plus 4I sine t minus 2 sine t. Okay. So I don't know. So, okay, there's a trick that maybe you learned, maybe you didn't. It just saves a lot of time. So you know how generally, you know, we would have two eigenvalues, right? So we'd have e to lambda 1t times v1 plus e to lambda 2t times v2. And for complex eigenvalues and eigenvectors, you would just take the complex conjugate. So, right, your initial lambda 1 is negative 2 plus I times t times 3 minus I, 4 plus 2I. Well, then you basically know that your second eigenvalue is going to be the complex conjugate of that. So negative 2 minus I times t times 3 plus I, 4 minus 2I, complex conjugate of this as well. So what you could do is you can apply this expansion where we expand e to the it into this cosine, multiply here, then do the same thing over here, and then add them together. Or a faster way to do this, which is provable, but with just more algebra, the easier way is to take this expression here, which we only did for one eigenvalue, an eigenvector, and we take the real part of it, which is 3 cosine t plus sine t, and 4 cosine t minus 2 sine t, and then we split them into the real and imaginary components. So this is the real part of this giant thing. Okay, and now we have negative 2t times I times negative cosine t plus 3. Oh, sorry, this should be a sine t. I didn't multiply correctly. Okay, plus 3 sine t. And then 2 cosine t plus 4 sine t. Okay, this, right, these correspond to the imaginary components of this, right? I picked out 4i sine t and 2i cosine t, and 3i sine t and negative I cosine t, and that gave me this right here. So if I split that into the real imaginary components, then the real solution is going to correspond to this part and this part, not including the I, so this part. So these are the two solutions that will satisfy this differential equation. So then we can write this in terms of its actual solution form, which is e to the negative 2t times this real part plus times c1 constant plus c2 times e to the negative 2t times the imaginary part, which is just this giant thing here. So this is just a shortcut. Instead of doing all this, you can just take the take one eigenvalue and eigenvector, expand it here, and then take the real and imaginary components of it and split those into two separate vectors. And those will constitute your solution to the differential equation, which you can write then in this form. So that gives us which answer choice. So we have 3 cosine t. So I think it's this one. Yeah. So this then corresponds to this answer choice here. So the answer is D. Uh-oh. Okay, in this problem we have find the least square solution for Ax equals B, where A is this matrix and B is this vector. So just a little thing about least squares. This is just the solution X that minimize the distance between Ax and B. So we want this to, I'll just write that down because it's useful to know if I can write. It minimizes ax b distance. Okay, and so the way we do that is we multiply both sides by A transpose, and then we solve for x. So A transpose, right, we just flip this matrix across the diagonal. We get 1, 0, negative 1, 1, 2, 2, times 1, 0, negative 1, 1, 2, 2. Okay, x equals A transpose times B, which is 1, 0, negative 1, 1, 2, 2, times negative 5, 0, 1. Okay, so when we do that multiplication, we get 6, 3, 3, 5 times xy equals negative 3, 2. Okay, and now what we can do is we can just solve this matrix for xy. So how do we do that? We just do our typical row reduction. So I can just do I think it honestly might be easier if we just did like the normal system of equations. So I guess you could do row reduction, but I just think this is easier. Equals negative 3x plus 5y equals 2. And then if you're really pressed for time, you can just literally plug in these numbers in, see which ones work. So in this case, okay, so I kind of know the answer already, but it's going to be C. So 6 times negative 1 plus 3 is equal to negative 3. And 3 times negative 1 plus 5 equals 2. So this is going to be our answer. You could alternatively row reduce. It just, I don't know. Actually, okay, honestly, it might not be that bad, because if you row reduce, you could do 2 times this row minus this row, and that would give you, that, okay, let's see, 2 times, so it would be 0, twice of 5, so 7, 2 times 2, 4 minus 3 is 7. So now it would just give you that this has to be 1. And then from there, you would be able to tell that, 0, negative 3 minus 3 is negative 6. So then you would know that it has to be negative 1 and 1. So I guess you could also reduce, but if you're at a loss, just plugging in some answer choices and seeing which ones work is also fine. So the answer is C. Okay, which of the following matrices is not diagonalizable over the real numbers? So how do we know if a matrix is certainly not diagonalizable? Okay, so wait. So we know that a matrix will be diagonalizable if it has distinct eigenvalues. So that's the quickest way to check. The other way to check is if you want to see the algebraic multiplicity, or the number of times that the eigenvalue appears in the characteristic polynomial, is equal to the geometric multiplicity, which that is just a number of linearly independent eigenvectors that correspond to that eigenvalue. So, you could check if the algebraic multiplicity of each eigenvalue is equal to the geometric multiplicity of each eigenvalue. That's kind of text, so we don't really want to do that. So it's easier then to just use use what we know, which is that if there are distinct eigenvalues, then it is for sure going to be diagonalizable. And then we can just find the eigenvalues, which is a bit of a faster process. So right, for A, just to reiterate, to find the eigenvalues, we do determinant of A minus lambda I, set equal to 0, solve for lambda. In the first one, we have 1 minus lambda, 2, 2, 5 minus lambda. Okay, so lambda squared minus 6 lambda plus 5 minus 4, which is just plus 1. Okay, so clearly this is going to give you 2 different eigenvalues. So we know that these are going to be distinct eigenvalues. So this is going to be diagonalizable. Same thing here. We can find the determinant of this. So, we have 1 minus lambda. Maybe I should write this out. 1 minus lambda, 3, 5, 0, 0, 4 minus lambda, 1, 1, 4 minus lambda equals 1 minus lambda times, I'm going to expand down this column, 1 minus lambda times lambda squared minus 8 lambda plus 16 minus 1, which is just 15. Okay, so this can be factored into okay, so that gives me 3 distinct eigenvalues, so that's going to be diagonalizable. If I lost anyone with the determinant thing, I just did 1 minus lambda times the determinant of this, because you delete the row and the column that your entry is in when you find the determinant, and then you take the determinant of this. And then because I'm expanding down this way, these zeros are just going to mean that I don't need to do anything else apart from this first expansion. Okay, so now for the third part, we have, for the third thing, we have this matrix here, and this is, I think, an upper triangular matrix, which means that you have non-zero entries on this half, and then you have 0 entries only on the bottom half of the triangle, and that just means the eigenvalues will just be along the diagonal, so 1, 2, and 10. Okay, so that seems reasonable. So those clearly seem like different numbers, so this is going to be diagonalizable. So that means it's not okay. That just means it's diagonalizable, so it's not going to be C. And so for D, we have this kind of ugly matrix here. I guess we can do this one. So 5 minus lambda. Maybe this is just an exercise of determinants. Okay. I'll just expand along this row, and I'll do 5 minus lambda times this, which gives me 2 minus lambda, 1, 1, 2 minus lambda, minus 3 times 3 minus, not 3 minus lambda, 3, 1, 4, 2 minus lambda, plus 4, and then gives me 3, 2 minus lambda, 4, 1, 5 minus lambda times lambda squared minus 4 minus 1 is 5, minus 3 times -3 lambda minus 6 minus 4, so that's minus 10. Plus 4 times 3 minus, so 3 plus 4 lambda minus 8, so 4 lambda minus 8. Wait, minus 5, I think. Okay, so we can just start adding these together. Okay, and that gives us 25 lambda minus, or 25 lambda plus 10. And this gives us like lambda cubed plus 5 lambda squared plus 30 lambda minus 15 equals 0. And so after checking with Wolfram Alpha, I realized that this is actually not easily factorable. So I'm not entirely sure how you're going to figure out this is diagonalizable. But on the bright side, you do have another answer choice that is certainly going to show that it's not diagonalizable. So I'm just guessing this is maybe some answer to trick you or to waste your time, kind of like I just did. So maybe we just skip this and move on to the other answer choice and look at what that gives us. So this is another upper triangular matrix where you have the eigenvalues on the diagonal. It's already suspicious because it has 2 repeated eigenvalues, so that should be a warning sign. So now we have this is potentially not diagonalizable. However, if you really wanted to check, you could confirm this by checking if the algebraic multiplicity and geometric multiplicity are different. So, for example, we know one of the eigenvalues is going to be 1. So 0, okay, that's a bit sudden. When we plug this into a minus lambda I times x equals 0, we have 0, 2, 3, 0, 7, 7, 0, 0, 7. Okay, and then we set that equal to 0. And we end up with, you know, some constraints. So we have, let's do this. Zero, 0, 1, 0, 1, 0, 0, 0, 0. So you can see how this can ultimately be row reduced into this form if you just do some division and subtraction and whatnot. And so you can see that, you know, one of the eigenvectors that will satisfy this is first eigenvector of 1, 0, 0. Because these 2 entries have to be 0. So then for lambda equals 8, then we have 1 minus 8 is -7. 2, 3, 0, 0, 1, 0, 0, 0. Okay. So this gives us the 7 to 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. So our first eigenvector can be so the last entry has to be 0. But then our other two entries must satisfy this condition where negative 7x plus 2y equals 0. So I could have, you know, 2, 7. But this kind of limits me, and I can't really create another linearly independent eigenvector of this one. So that means that my geometric multiplicity is going to be 1, because I only have one linearly independent eigenvector that I can create from this. And then I also have an algebraic multiplicity of 2 for the eigenvalue of 8. And just to reiterate, I was not able to figure out, I cannot really create another linearly independent eigenvector just from this alone, because I'm already constrained in this component, so the z component, and my x and y's are constrained. So I cannot come up with anything that's going to be linearly independent of this eigenvector. Just to explain this again, first of all, because of the constraint from this as well as this constraint here, we know that we are only able to find one eigenvector that is linearly independent for the eigenvalue of 8. Secondly, this means that our geometric multiplicity is going to be 1 because we only have one linearly independent eigenvalue. And then we know our algebraic multiplicity is going to be 8 because 8 appears 2 times in the eigenvalues, right? Because from here, we see that we have 8 as our eigenvalue twice. So that means the algebraic multiplicity is 2. 2 is not equal to 1, so the algebraic multiplicity and geometric multiplicity do not equal each other, so that means that this is not diagonalizable over the real numbers. So you know that this is not going to be diagonalizable, which it kind of already should have been a hint based on these expressions here, based on the repeated eigenvalue. But you should always, I think it's always best to confirm that with the algebraic multiplicity and geometric multiplicity, because sometimes there are eigenvalues which are repeated, but you are actually able to find 2 linearly independent eigenvalues for them. So in this case, we should just check to make sure. And then for D, I really do not know how you are supposed to determine this is diagonalizable without a calculator. So maybe it's just the strat to look at all your answer choices before you do an annoying calculation like this. So the answer is D or E. Okay, so let v1 equals this, v2 equals this, and v3 equals this vector, and this is an orthogonal set that spans R to 3. The vector x is written in this form. What is C2? Okay, this is just a row reduction problem in disguise, so we can just put this into our augmented matrix form pretty quickly, where you have 0, 3, 4, negative 5, negative 4, 3, 5, negative 4, 3, 10, negative 10, 20, and you just start row reducing. So I'm just gonna, okay, so I'll divide the first row by 5. That gives me 0, negative 1, 1, 2. Then I'm gonna add row 2 and row 3. So this gives me 7, negative 1, negative 1, and then 10. And then I'll just leave this one as is. Okay, and then I'm just gonna add row 1 and row 2. Wait, actually no. I'm gonna do row 2 equals row 2 minus row 1. So that will give me 7, 0, negative 2, 8, 2, 1, negative 1, 0. And then I'm just going to divide the third row by 3. So we'll get 4 thirds. Actually, I don't want to do that. I'm just going to keep the third row as is. Okay, and then I'm going to divide the second row by 7. So 1, 0, negative 2 sevenths, 8 sevenths, 0. And I'm also going to divide the first row by negative 1, 1, negative 1, negative 2. And then now that I have that, I'm going to do 4 times... Okay. Now that I have these two rows as this, I'm going to do row 3 minus 4 times row 2 minus 3 times row 1. So what does that give me? Something very long and annoying. Okay, 1, negative 1, negative 2, 1, 0, negative 2 sevenths, 8 sevenths. Okay, so 0, 0 here. So 3 minus 4 times row 2, 8 sevenths, minus 3 times negative 1. So that's 6 plus 8 sevenths. Okay, 50 over 7. Great. So then we have 20. Now we're looking at this entry here. So 20 minus 4, so 32 sevenths, minus 3 times negative 2. Oh gosh, okay. So 20 minus 3 sevenths. 26. So that's 140 minus 32 plus 42 sevenths, which is just 150 over 7. 150 over 7. Okay, and now we can do some good row reduction where we divide the last row by 50 over 7. That should give us 3 here. And then we would then eliminate everything here. So we do 2 sevenths. So you'd add 2 sevenths times this row to here. So when we do that, that's 6 over 7. So that's just 0 and then 2. And then for the top one, we would do this row plus this row. So it'd be negative 2 plus 3, which is 1. Okay, so C2 is just going to be 1 then, because that's... Okay, this is like kind of not ordered right, but this entry corresponds to the C2, because when we write it as C1, C2, C3 here. So whatever entry this corresponds to is going to be C2, so our answer is A. As a side note, if you have forgotten why we put things in augmented matrix forms like this, so the way that we do this is, right, when we have C1 times V1 plus C2 times Z2 times C3 plus V3, we really just have a system of equations, right? We have, you know, C1 V1 is just, so if we just look at the top terms right here, we have 0 times C1, so C1 times 0, plus C2 times negative 5, plus C3 times 5 equals 10. And we go down the row, right, and we have C1 times 3, plus C2 times negative 4, plus C3 times negative 4 equals negative 10, and onto the last one and stuff like that. So really, this is just a system of equations that we're then putting into this form right here. And so that's why we just automatically put the columns here, and then we just put the columns automatically like this. I don't know, this confused me at one point in my life, so I just thought it'd be worth mentioning again, because it's really just a system of equations that we're just putting in this form to row reduce. So yeah. So this question says, suppose that A equals this matrix, which is equal to P dP transpose, where D is diagonal and P is an orthogonal matrix. So find P and D. Orthogonal matrix, what does that mean? So it basically means that if you have an orthogonal matrix, one property is that the transpose is equal to the inverse. So really, P transpose is just equal to P inverse. That should look really familiar as the diagonalization thing, where you are going to diagonalize A, and that gives you the eigenvalues in this matrix and the eigenvectors in this matrix. So how to figure this out? So first we should find the eigenvalues of A. So we take the determinant of A, 3 minus lambda, 0, 1, 0, 4 minus lambda, 0, 1, 0, 3 minus lambda. Set that equal to 0, and then solve for lambda. So we get 3 minus lambda times 3 minus lambda times 4 minus lambda minus 0, because I'm just going to expand along this column, and then plus 1 times the determinant of 0, 1, 4 minus lambda, 0, equals 3 minus lambda times 3 minus lambda, So I'm just going to factor out the 4 minus lambda just to make our lives easier. And this determinant ends up being 0 minus 4 minus lambda, which is just minus 1 then here. Okay, so 4 minus lambda, lambda squared minus 6 lambda plus 9 minus 1 is 8. So this gives us 4 minus lambda times lambda minus 4, lambda minus 2. Okay, so our eigenvectors, our eigenvalues are going to be 4 and 2. So automatically we can just get rid of these two because it just does not make sense. So then we need to now find the eigenvectors. So we do that by plugging in lambda equals 4 into the expression a minus, in this case, 4i times x equals 0. Okay, let's do this. So 3 minus 4 is negative 1. 0, 1, 0, 0, 0, 1, 0, negative 1. Okay, so these are clearly multiples of each other, these two rows. And so I'm just going to get rid of this, so it just becomes a row of zeros. So an x that satisfies this is going to be, 1, 0, negative 1. Wait, no, 1, 0, 1. 1, 0, 1. And then notice that we kind of have this constraint. We don't have this constraint on this second variable. So that could be anything. So I know that lambda equals 4 is repeated. So I need to find 2 linearly independent eigenvectors corresponding to lambda equals 4 because it's has an algebraic multiplicity of 2. So I need to find another one, and that one I can just write instead as 1, 1, 1. I can also write that as 0, 1, 0 because this will also satisfy this expression right here, which, if we want to remember, is negative x plus z equals 0. So x and z can be 0, and then y can just be anything, and that will be linearly independent of this one. So we now have 2 linearly independent eigenvectors for lambda equals 4. So let's find one for lambda equals 2. So then our a becomes, so 3 minus 2 is 1, 0, 1, 0, 2, 0, 1, 0, 1. Okay, what's the constraint on this one? So notice that these are again multiples of each other, so I can just get rid of this one. I can make this a 0, and I'll make this a 0. And then this means that our y entry has to be 0, so this has to be 0. And then this expression, which is just x plus z equals 0, means that we would have to have like a 1 or a negative 1 here, say, for example. So now we have 3 linearly independent vectors, eigenvectors. So we have 1, 0, 1, 0, 1, 0, and 1, 0, negative 1. And we clearly answer choices. And also, I think we can eliminate this one because this is not right. We have 2 4s and 1 2. Okay, so remember that when we put this into our diagonal matrix form in the P matrix, we need to put them corresponding to the same eigenvalues. So right here we have 4, 4, 2. So then the columns that correspond to those need to be corresponding to the eigenvectors. So here we have for 4, we have these, actually it's a different color, it's kind of confusing. So here we have, for 4, we have these 2 eigenvectors. So we have something like this. So we need these 2 to correspond to x1 and x2 in some way. So hopefully, okay, we did not normalize this, but hopefully you can just see that if we did normalize this, we would just divide by the magnitude of the vector, which is just, maybe I'll just write it out. So we would do 1 over square root 1 plus 1 times 1, 0, 1, because this normalizes everything here. So then we end up with 1 over square root 2, 0, 1 over square root 2. So that's just a normalized version of our eigenvector. But anyways, you can see here that these 2 eigenvectors, which are the columns of P, correspond to this, whereas for this other option, we have this one here and this one here, but this is not an eigenvector corresponding to lambda equals 4. So because of that, this is not going to be the right solution because your columns which contain your eigenvalues must correspond to the columns that are the eigenvectors of that corresponding eigenvalue. So from this, you can see that A is going to be our answer. An additional thing that we can again check with is to see for lambda equals 2 if this eigenvector corresponds to this eigenvector. Again, you can see that it does because even though the negative sign is on the wrong term, or it's in the other term, it doesn't matter because our eigenvector can be anything that satisfies this expression. So even if we picked -1, 0, 1, that would still satisfy this expression, so it's still valid as an eigenvector. So just recognizing that is important. But again, you can see that for the eigenvalue of 2, it does correspond to this right here, but just normalized version of this. So you can see that the eigenvectors in this solution correspond to its respective eigenvalues. So that's why the answer is A.
Okay, which of the following statements is always true? All matrices are real matrices. This is a key point because I think if you have complex or something matrices, then some of these statements might not apply. So let's just focus on the real matrices. If A is a symmetric matrix, then A always has n distinct eigenvalues. A symmetric matrix is one where if you flip it along the diagonal, then you get the same matrix. So that means that, if you have A is equal to A transpose. So an example of a symmetric matrix would be 0, 0, 0, 0. A always then has n distinct eigenvalues. So the keyword here is distinct. So here, hopefully you can see that the eigenvalues are going to be both 0. So you don't have 2 distinct eigenvalues, you only have 1. So this is not a true statement. If A is symmetric, then A squared is orthogonally diagonalizable. So from the spectral theorem, we know that if a matrix is symmetric, then it will be orthogonally diagonalizable. So is A squared orthogonally diagonalizable? So A squared is going to be A times A, right? And that's going to be equal to, because A is symmetric, A equals A transpose. That means A transpose, A transpose. So A dot A is equal to A transpose times A transpose. Sorry, not dot. A times A is going to be equal to A transpose times A transpose. So that means that A squared equals A transpose squared. So that actually means that A squared is also symmetric. Because it's also symmetric, then we can use the spectral theorem and say that that means it will be orthogonally diagonalizable. So this is actually a true statement. In 3, we have if both A and B are orthogonally diagonalizable, then so is AB. So if something is orthogonally diagonalizable, that means that it can be written in this form, right, where you have some orthogonal matrix, which I'll call UA, times your diagonal matrix times your UA transpose. It can be written in this way. And then let me just write, this is orthogonal matrix. Okay, and then we also have B, which is also orthogonally diagonalizable, so that means it can be written as UB, DB, UB transpose. Okay, now let's look at AB. So AB is then equal to UA, DA, UA transpose times UB, DB, UB transpose, which I'm just plugging in A and B here. And then when we look at this, it does not seem like it can be written in a form, U times D times U C transpose. Because if we can write it in this form, then we know for sure that it is orthogonally diagonalizable. But in this case, just even looking at this, we're trying to group these together. In the ideal world, right, this term would become the identity matrix, which would give you some diagonal matrix and a diagonal matrix, which gives you another diagonal matrix. And then you're bracketed by some orthogonal matrix and then the orthogonal matrix transpose. But the problem here is that A and B are different. So that's why we have, UA, DA and DB and UB. So first of all, UA transpose times UB is not going to be equal to the identity matrix. You can't confirm that. So already we have a problem. And then on these sides, we have UA and then UB transpose. So we can't really argue that those will definitely be the same because A and B are just two random matrices that happen to be orthogonally diagonalizable. So we can't really say anything about the relationship between UA or UB or DA, DB or the transposes of them. So because of that, we cannot say that AB is going to necessarily be orthogonally diagonalizable just because A and B are. So this is false. If A is symmetric, then any two eigenvectors from different eigenspaces are orthogonal. Okay, this is a kind of weird statement, but we know that A times V1 equals some lambda 1 times V1, let's say. So where V1 is going to be an eigenvector from one eigenspace, and then V2 is a eigenvector from a different eigenspace. Because they're from different eigenspaces, lambda 1 is not equal to lambda 2. Right? So we're trying to see if their eigenvectors are orthogonal, so we're trying to see if v1.v2 is equal to 0. Okay. Looking at this, we see that we have AV1 here, so why not multiply both sides by AV2? Right, so we take the dot product with V2. We also do a dot product here. Okay. The trick with the dot product, right, is that we have, if we have, for example, y dot y, where y is this matrix here, then we can write y dot y as y transpose times y, where y transpose is this matrix here, and then y is this, right? So this is just how we write dot products in multiplication form. So because of that, we can actually write this side as a v1 transpose times v2 equals lambda 1 v1 v2 dot with v2. Then we can apply a transpose rule, which is AB transpose equals B transpose times A transpose. And that gives us V1 transpose times A transpose times V2. And that is equal to then lambda 1 times V1 dot V2. So now we can rewrite this form, right, V1 transpose times A transpose times V2 into dot product form. So we do V1 dot product with A transpose V2. Okay. Just to explain how we got there, remember that if we have, y dot y, we can write it as y transpose y. Well, we can also flip it around, right? If we have some y transpose times y, we can rewrite that as a dot product. That's what we did here. We had v1 transpose, and then we have a transpose times v2. So we just put that back into dot product form, where we have v1 dot product with a transpose times v2. Okay, so now we have this expression here. And we know that because A is symmetric, A transpose equals A, right? Because it says A is symmetric. So that means that we have V1 dot product with A V2 equals lambda 1 V1 dot V2. Okay, and then we know that A V2 equals lambda 2 times V2, right? So we can rewrite this now as V1 dot lambda 2 v2 equals lambda 1 v1 dot v2. Okay, then we can rewrite this whole thing as lambda 2 minus lambda 1 times v1 dot v2 is equal to 0. Oh, that's to 0. Alright, we just subtract things over because lambda 2 and lambda 1 are scalars, so we can just take those out. And then also v1 dot v2, it's the same. So even if you reverse the dot product, it gives you the same result. So we end up with this expression here. And we know that these eigenvectors are from different eigenspaces. So that means that lambda 1 is not equal to lambda 2. So the only way for this equation to be satisfied is if v1 dot v2 equals 0. So that means that these eigenvectors are orthogonal. So this is a true statement. And just to recap how we got there, we used information about the eigenvectors, and then we tried to multiply or take the dot product of both sides. So we chose this equation. We took the dot product of both sides with v2, and then we ended up doing some fancy manipulation to end up with this expression here. So we know that this is going to have to be satisfied for the information we're given. And so we know that v1 dot v2 then has to be equal to 0. And that proves that the two eigenvectors are orthogonal. So 2 and 4 are our correct statements, so the answer is going to be E.
Okay, in this problem we have f and g, which the inner product is defined by this integral. And if one performs a Gram-Schmidt process to the polynomials, then the resulting orthogonal basis of the span of t squared and 1 is what? Okay, so this is really performing the Gram-Schmidt process, but now with inner products instead of dot products, which, if you remember, for vectors, when we do the Gram-Schmidt process, we take the dot product of things. And so here we do the inner product because it's polynomials. Okay, the way to do the Gram-Schmidt process is you first pick a polynomial to just stay the same. So from these answer choices, it seems very likely that they picked t squared as the one that stays the same. So I'm going to I'll first define these as u1 and u2. I'll pick our first orthogonal basis term to be u1, so t squared. And the way you find the second one is you do u2 minus the projection of u2 onto v1. So that's just going to be equal to u2 minus the inner product of u2 and v1 over the inner product of v1 times v1. Okay, so that's just equal to 1 minus the inner product of 1 and t squared and divided by the inner product of t squared and t squared times t squared. Okay, these are v's and this is a u. I'll try to denote my u's with like this, but yeah, so my v1 is t squared, not t2, so t squared. Okay, so what is the inner product of this? So 1 t squared is going to be equal to, from this, integral from 0 to 1 of 1 times t squared dt, which integral is just 1/3 t cubed 1 0, evaluated at 1 and 0, so that just gives us 1/3. Then t squared is equal to integral 0 1 t squared times t squared dt equals 1/5 t to the 5th, evaluated at 1 and 0, which is just 1 over 5. So this expression becomes 1 minus 1/3 over 1/5 times t squared, which is just 1 minus 5/3 t squared. So this is going to be our v2, and our v1 is this. So our orthogonal basis is going to be c, t squared and 1 minus 5/3 t squared. Oh, great. Okay, so we have the Gram-Schmidt procedure again. Okay, now we just get to do this, but with vectors. So we have u1, u2, u3, and we want to essentially replace these with this orthonormal basis. I guess one initial check you could do is to see if all these vectors have magnitude of 1, but just from looking at them, it kind of seems like they do, so I'm just not going to check that. So the way we do this for vectors is to first, first we set one vector as being equal to it's just going to stay the same, but we just normalize it because it needs an orthonormal basis, which means that not only are the vectors orthogonal to each other, but they all have magnitude of 1. So I'm just going to pick, so I want to find v1, v2, and v3. So v1, I'm going to set as equal to u1 divided by the magnitude of u1, which is going to be 1 over, right, so 1 squared plus -1 squared plus 0 squared is just 2. So then I square root that to get the magnitude, times the u1, which is 0, 1, -1. To find v2, I do u2 minus the projection of u2 onto v1, which is equal to u2 minus u2 minus u2 dot v1 over v1 dot v1 times v1. Okay, so that just is equal to -1, 0, 1 minus u2 dot v1 is -1, 0, 1 times 1 over square root 2 times 0, 1, -1 times 1 over square root 2 times 0, 1, -1. Same thing because it's v1 dot v1 times v1. Okay. negative 1, 0, 1 is equal to. So v1 is already normalized, so we would know that v1 dot v1 is just equal to 1. You can also just do the dot product, 0 times 0, 0 times 0, 1, 1, negative 1, negative 1, times 1 over 2 after you multiply these two together. So this just gives you 1. And then you have here, I don't know why I put v1 here. I can just write out v1 as 1 over square root 2, 0, 1, negative 1. So negative 1, so now let's do the dot product of u2 and v2. That gives you 0 plus 0 minus 1. So negative 1, and then times 1 over square root 2, times 1 over square root 2, 0, 1, negative 1. This just gives you negative 1, 0, 1, minus, or I guess plus 0, 1 half, negative 1 half. And that is equal to 1, 1 half, 1 half. Okay. Now we want an orthonormal basis. This means the magnitude needs to be 1. This magnitude is definitely not equal to 1. So what we do is we divide by the magnitude of the vector. So that means we do 1 over square root of 1 plus 1/4 plus 1/4, because I just squared each of these components and add them together. And then I multiply it by the original vector, negative 1, 1 half, 1 half. Okay, so this ends up being square root of 2 over 3 times negative 1, 1 half, 1 half. Which I can then simplify to negative 2 over square root of 6, 1 over square root of 6, 1 over square root of 6. And I'll set that as my actual v2. So basically from these first two vectors that we get in the orthonormal basis, you can eliminate some options. First of all, this is definitely not right. There's nothing like this or this at all in any of these. Our first one is 0, 1 over square root 2, negative 1 over square root 2, so these still work. But then we have this as our v2, which matches with this one only. So it seems like these two are wrong, so it seems like our answer is C, which it is, but let's also do v3 just so we can get more practice with this fun procedure. So we have u3 minus the projection of u3 onto v1 minus the projection of u3 onto v2. That's equal to u3 minus u3 dot v1 over v1 dot v1, so u, times v1 minus u3 v2 over v2 dot v2 times v2. Okay, great. Okay, so u3 is 1, negative 1, 1 minus u3 dot v1, so 1, negative 1, 1 dot with v1. What's this thing right here? 0, 1, negative 1 divided by v1 dot v1. v1 is already normalized, so we've already argued that v1 dot v1 will be 1. You can do the math yourself if you want. Times 1 over square root 2 times 0, 1, negative 1 minus u3 v2 over v2 dot v2. So what is that? Okay, 1, negative 1, 1. Okay, times negative 2 over square root of 6, 1 over square root of 6, 1 over square root of 6. v2 here is normalized, so we just know this is going to be 1. v2 dot v2 is equal to 1 times negative 2 over square root of 6, 1 over square root of 6, 1 over square root of 6. Okay, that gives us 1, negative 1, 1 minus, okay, negative, wait, 1 times 0, negative 1, 1. So this dot product gives us 1 half. Okay, so the coefficients give us 1 half, and then the dot product gives us negative 2 minus, oh dear, so negative 2. So we get negative 2 over 6 from a dot product times negative 2 over square root of 6 1 over square root 6, 1 over square root 6. Okay, and that should give us 1 negative 1 plus 0, 1 negative 1 plus 4, 6, 2, 6, 2, 6. Okay, I think I'm reading a negative here. Yeah, okay. And then we add that together, that should give us 1/3, 1/3, 1/3. We need to normalize this because it wants an orthonormal basis. So 1/3 squared plus 1/3 squared plus 1/3 squared is going to be 1 over 9. Yeah, so it should be 1 over 3. Square root that. Okay, that was not very clear at all. So to normalize this, we do 1/3 squared, and then we just have 3 of those. So we do this. Multiply that by 3. Square root that over 1 by 1/3, 1/3, 1/3. So 1/9 times 3 is 1/3. So we just get in the square root, we have square root 1 over square root 3. Multiplying that out, this gives us just 1 over square root 3, 1 over square root 3, 1 over square root 3 for our v3. And so that very clearly corresponds to this. So our answer is C. And that is the end of the exam.